In this video, I want to introduce simple linear regression, and I'm going to do this using an example. If you recall from our previous lecture on exponential smoothing, we estimated the initial parameters for the Holt-Winter model. Remember, that's the one with the level, trend, and the seasonality. And when we're initializing, we removed the seasonality, or we deseasonalized the demand in order to estimate that initial level and trend. And what I told you at that point is that we used regression to come up with this relationship, which was an estimate of what the initial intercept would be and what the trend would be. And we came up with this nice linear equation that described this line. So what are we doing with regression? Well, all that we're really trying to do is come up with a linear relationship that describes the behavior of this dependent variable given the behavior of this independent variable, x. And in this case, my y is daily demand of bagels, and my x is the time period. And the data that I used went from time period 80 to time period 99. So we have historical data, and I've got pairs of data, observed values, so I know for each of those time periods how many bagels I sold, that's the y. I know what the time period was, that's the x sub I. And what I want to do is I want to estimate what the intercept is and what the slope is. Those are unknowns. I'm going to use the observed data to try to estimate that. Now I've also got this error term that we're going to call residuals, and that's something that will always be unknown, but I want to minimize that because at the end of the day I'm creating this equation, and this equation is simply saying my expected value of y, bagel demand, and for daily bagel demand, given a certain time period x, is equal to that beta naught intercept plus beta 1 slope times my time period. So the relationship is always going to be a linear model. We're using existing data, these pairs of data, xi and yi, to find the best fit. And how do we know what's the best fit? Well, we're going to look at the error term for this. The error term is that unaccounted or unexplained portion of the model. And we assume, just like in exponential smoothing, that they're going to be independently and identically distributed, normally with a mean of 0 and some standard deviation. Why does it have to be a mean of 0? Well, if it wasn't, it'd be biased, right? So you want to make sure your errors have a mean of 0. They bounce up and down around your estimated value. So this is what we came up with in our data. And let me just point out a couple things here, just to make sure everyone understands. So this point that I just circled is for time period 97, and that's the observed demand. And so we sold 204 bagels on the 97th day on that time period. So that's y sub 97 equals 204. Now if I look at my estimated model, what did I predict based off this linear model we'd sell? Well, I just plug in time period 97 to this equation. And so I'd come up with 188.4. So we estimated or forecast 188 bagels sold. We actually sold 204. That means my error or residual for that one observation is 15.6, just the difference. And I could do this for each one of the observed values. And what I'm trying to do is to find this line that minimizes those residuals. So that's the whole thing that ordinary least squares or regression does. We try to minimize the residuals because those are the differences between what actually happened minus what we predicted. So we want to find the b's. Remember, we're estimating these b naught and b1. And why do I use lowercase b's instead of the betas? Well, that's simply because these are sample, these are estimates rather than the theoretical values. So in any case, I'm trying to determine this b0 and this b1. And I want to do this by minimizing the residuals. And I could do this a bunch of different ways. I could say, okay, pick the b naught and b1 so that the sum of all the errors is as small as possible. Or I could say, pick the b naught and b1 such that the absolute value of the errors is a minimum. But what's typically done is we minimize the sum of the squares. And so what is that? Well, I just simply take the error term, square it, and I'm going to minimize the sum. So you can see it's this equation right here, where this is the observed demand for period I, and I'm subtracting off what I estimated, my prediction, beta naught plus beta 1 times x1. So squaring each of those and summing them up, I want to minimize that value. I want to find the B0 and the B1 that minimize that equation. So how do I do this? Well, you can use partial differential equations to find first order optimality conditions with respect to beta naught and beta 1, and then you set them equal to 0, and you solve for them simultaneously, two equations, two unknowns. And luckily, I won't make you go through that, but you end up with these two equations. And these two equations are the determination for the slope and for the intercept term, such that the sum of the squares of the errors is at a minimum. And so we'll use each of these to show, and we'll use those to estimate what this line is. So one last point before we go into how to actually solve these is we look at the data, and we know from the data that the mean, this x bar of the time period, is 89.5, right? That's just the mean between the sample data from 80 to 99, so it's right here. And I know the mean of the number of bagels I sold per day is about 157.4, that's right here. Well, by doing this line, I also know that I will always go through that point. I will always go through the point that is x bar, the mean of the x values, y bar. My line will always go through there because what I'm doing is I'm minimizing these things around the average. And so it's just a fine point. As I get closer, my estimate is always going to be more accurate as I'm closer to those mean values. As I get further away, we'll see my confidence gets a little lower. Anyway, now what I want to do is show you how to solve those in spreadsheets.